So, that's it. We are glad to have with us today Dr. Charis Anastopoulos from the University of Patras. His research field is in theoretical physics and specifically on quantum theory, which, as you know, the last years is also a field of research also in our institute. So we are very glad to be about to start listening to his talk. And you see already the title on your screen, Gravitational Effects in Macroscopic Quantum Systems. So you may start. And thank you.
Thank you for the opportunity to give a talk in your group. So I'm going to talk about gravitational effects in macroscopic quantum systems. First, let me explain why this is an interesting topic. We all know that there is a conflict between our two fundamental theories, meaning quantum theory and general relativity. It's a conflict, conceptual, technical. There are two different theories with different concepts, different mathematical formulations, and there are many programs trying to unite them. Still, we're very far from a complete theory. And the dominant idea is that quantum gravity effects become important at the Planck scale, which is well beyond our experimental reach. On the other hand, there is another domain, not the high energy domain, but the macroscopic quantum system domain, where we can see the interplay between quantum systems and gravity. And this is weak gravity and low energy, but macroscopic quantum phenomena. And in the next decade, we expect to have a lot of feedback, experimental feedback, from this type of systems. So this talk is mainly about, is an introduction to this field of research, which we expect to be driven by experiment very soon. Now, are there any experiments about that concern gravity and quantum? Well, the first experiment, which involves both gravity and quantum, was the famous Colella-Verhauser-Werner experiment in the 1970s. So what they did is essentially they showed that neutrons moving in gravitational fields, they obtain a phase when you do an interference experiment, an interference phase. And this is important because it shows that an external background gravitational field can be treated as a potential in non-relativistic Schrödinger equation. Well, you may say this is what one would expect, but still it was the first direct experimental confirmation that gravity acts as a potential, that an external gravitational field. There are a few other experiments ever since that demonstrate this point, but there is no experiment that tests how a quantum system will gravitate. This means what is the gravitational force that is generated by quantum distribution of matter, meaning quantum distribution of matter, meaning a distribution of matter that is characterized by strong quantum effects like interference of macroscopic distinct states, and what is the gravitational interaction between two different quantum matter distributions. These are the type of experiments, these are that we expect to see in the coming decade. Now, what do we expect then? How would we expect a macroscopic quantum system to gravitate at the weak gravity limit, at the Newtonian limit? Well, weak gravity is very, very, very well described by Newton's theory, using the gravitational potential phi, and this is slave to the mass density mu through the Poisson equation. The potential is not dynamical in Newtonian theory, it is completely fixed by the knowledge of the mass density. So the simplest hypothesis is to say the same holds in quantum theory. So if we have quantum matter, what happens is that we get a mass density operator. Mass density becomes an operator. So if this equation holds, then also phi should be an operator, but not really a physical operator, because as I said, it's not dynamical. Not being dynamical does not transfer, does transfer to quantum theory. So eventually we are having a non-local term in the Hamiltonian of the system, which for weak gravity non-relativistic limit, which is the standard form for gravitational self-energy. Well, I miss a factor 1/2 here, but with quantum mass distribution. So how do we prove this? We can start from general relativity, take the linearized theory, quantize, and then take the non-relativistic limit, or we can take from the linearized classical theory, we can take the non-relativistic limit and then quantize. So this is assuming that the usual quantization rule. So this is an assumption, and this is why it is important to test this result to verify that this perhaps obvious assumption is true. And we will see that there are many people that doubt this assumption. Now, what is the Hamiltonian classically of the system in the non-relativistic regime? So the Hamiltonian has a term for the mass density, total mass. This is the kinetic energy part. And there is a part with the interaction with the Newtonian field. Here I call it gamma. And you have gravitational wave and interaction with gravitational wave. The Newtonian part, the Newtonian part is here. And gamma is fixed by solving the Poisson equation. So this is the classical Hamiltonian. If we ignore gravitational waves, all we need to do is to construct, to quantize mu. How do we do this? If you're not familiar, we can see easily how it is done in a field theory. In a field theory, you define the stress energy tensor as a quantum operator, taking the non-relativistic limit is relatively, it's much easier. So if you take a quantum scalar field and you take a massive quantum scalar field and you take the limit, the non-relativistic limit, you define two fields which are essentially the Fourier transforms of the A and A dagger in the non-relativistic approximation. So with these two fields, you can define the regularized mass density operator in this way, where F is a smearing function. So strictly speaking, it cannot be defined as in the classical theory. You need to regularize at very small distances, which is natural because the particles you are describing have a finite extent. So if you do this, you quantize, you get a non-relativistic quantum field theory that describes, and the Hamiltonian for this non-relativistic quantum field theory that describes the system. So this is the basis for the quantum description of quantum effects in weak gravity. I have to emphasize, assuming that the standard quantization rules apply. So what does this Hamiltonian, does this theory predict? Gravitational cat states. And this is where it starts becoming interesting. You can have superposition of states with the same mass, let's say, but macroscopically distinct mass densities. So this has no classical analog. And its component, of course, generates a different gravitational field through the Poisson equation. So it's a superposition of two macroscopically distinct states. And this is what needs to be constructed in the lab in order to test non-trivial gravitational quantum effects. Now, let me give some history about the gravitational cat states. There are some early discussions by Karolyi in the 60s, and then there is some discussion by Penrose and Yossi in the 80s and 90s. But these people mainly wanted to kill those states. I will explain why. They did not want such states, and they were looking for a mechanism to suppress them. The first work to actually talk about the possibility of measuring those states is by Baylock and I in about 6-7 years ago. So we coined the name of gravitational cat state, and we show that in principle it's measured with the next generation of experiments. The two groups by UCL and Oxford followed, who proposed the so-called BMV experiments, who became very popular. And they suggested that these experiments can prove that gravity is quantum. This has generated quite a lot of discussion. And some other work involves our prediction that we're going to see Rabi oscillations, which we believe to be the best indication of this type of interaction. And there are more ambitious statements that we might be able to see superposition of different causal orders of space-time events, essentially fluctuating light cones, as we would say. So what is a gravitational cat state? The simplest toy model is to consider a double well potential in which the two wells are separated by a macroscopic, well, mesoscopic distance L. Let's say L is of the order of micrometers. So this system can be shown that in some regime it is approximated by a qubit, a two-level system, and its Hamiltonian is just obtained from the tunneling rate between the two minima. And in this case, if you have a test particle and you try to measure what is the force exercised by this superposition state, you see the force will be different in the horizontal direction if the particle is here and if the particle is here. So essentially the force is again a dichotomic variable. It is equivalent to sigma 3 in the two-level system approximation. Oh, sorry. Press the very... Okay. And well, if we make a modeling of what we are going to observe, we are going to, when we measure this force F, you are going to get a time series of force measurements, and there is a prediction about a non-trivial correlator, which between those force measurements, that this is the prediction from standard quantum theory. So when is this going to be measurable? So we're talking about 2016, right? 6 years ago, we took the numbers of the best experiment, the state-of-the-art experiments for constructing superconducting, for constructing macroscopic superposition and for measuring weak forces. And we saw that the optimum combination is we are 4 orders of magnitude away from sensitivity. Again, this is optimistic, but still this shows that this type of phenomena are measurable in the near future in 1 or 2 generations of developing macroscopic quantum system physics. Certainly much easier than accessing the Planck scale. So how macroscopic can we have the quantum systems? Just a transparency showing some crucial results. You can have, for example, the superposition of beryllium ions at distance of 80 nanometers by the NIST group. This is about, let's say, 100 nanometers was the first, let's say, cat state in the nanoscale. And we can have atoms now. We can have delocalized wave packet of atoms at the scale of 0.5 meter, which is huge, which is completely macroscopic, but it's just the localization with not much control over this. We can have a 2-slit experiment with very heavy molecules at 25,000 atomic mass units at the 100 nanometers. And there is a hope that you might get superposition of superconducting microspheres in magnetic levitation at 10 to the 13 atomic mass units. This is very promising for testing this effect. Now, as I mentioned, this field became very, there was a lot of excitement by the proposal by Bose and the UCL group and Marletto and Vetrato from Oxford, who proposed that the gravitational interaction of 2 quantum systems will lead to creation of entanglement, and this entanglement between the 2 subsystems is measurable with desktop experiments. And there are several groups that are trying to construct the technology necessary for measuring this entanglement. Now, what made this claim very popular is the idea that this could be a proof of quantum gravity. I mean, this is the way it was publicized, I disagree. Well, many people disagree actually from the gravity community, because essentially this effect is due, as we said, to the Newtonian potential, which is not a dynamical degree of freedom of the gravitational field. So you cannot say that the true degree of freedom of gravity is quantized. You would need to see gravitational waves for that. So I'm not going to talk about this debate. It is still going on, different point of views, and I don't think it's essentially important, because there are other very interesting issues that can be explored in this experiment, rather than proving that it's quantum gravity. So, for example, to see this discussion about what is involved in this entanglement generation, consider the system I mentioned, two double well potentials separated by a distance d, one-dimensional systems. And so this is the geometry, and this particle is, you have two particles, one can be localized either here, and the other can be localized either here. Now, it is easy to show, it's again in the qubit approximation, it's elementary, that this type of system is characterized by Rabi oscillations, if you can prepare the state, with a frequency given by this quantity, this inverted omega. So essentially it's proportional to the gravitational constants, to the mass of the particle square, and some geometric, and divided by some geometric factor. If you don't have this parallelogram, you may have a circle, or you may have a triangle. So this factor will change, but essentially it's a length, 1 over some length scale. Now, if you just put numbers and you ask omega to be of the order of second, you see that you could observe Rabi oscillations, as you could observe entanglement creation, if you have masses in superposition higher than 10 to the 10th atomic mass units. As I mentioned, our current record, even though it's not very controllable, is about 25,000, a few orders of magnitude away, but the point is that there are several groups working, and they intend to construct, they're very much motivated by the test of gravitational effects, and they want to construct higher and higher mass superpositions. So in our opinion, the first foundational question that is settled by this experiment is how gravity interacts at the weak coupling limit. Does the classical statement that the gravitational force is slave to the mass density through the Poisson equation, does this remain true even in quantum theory? If yes, this is the conservative answer. If no, then this will have very profound implications, as I'm going to explain. So here are some references about this discussion about proving the quantum nature of gravity. As I said, in my opinion, it is implausible to talk about the quantum nature of gravity unless we have access to gravitons, and we don't have access to gravitons when we work at the level of Newtonian gravity. Last year, our group here in Patras, we did the first principle analysis of the system, starting from general relativity, linearizing it, quantizing it rigorously, trying to see how it depends on gauge fixing, and so on, and how it applies to this type of systems. We came to the conclusion, indeed, there are no true degrees of freedom in Newtonian gravity. There is an ambiguity in quantization in the time coordinates that we are going to assign to the quantum system. The assignment of time coordinates is not unique. This is known as a problem of time in quantum gravity, and it appears even at the weak gravity limit, which is very interesting, because this means that different theories of quantum gravity will probably make different predictions. And in principle, future experiments, not this generation, not the next, let's say in 30 years from now, might be able to distinguish between some proposals for quantum gravity at macroscopic quantum phenomena. This means you do not need to access Planck's length, you need to check macroscopic quantum systems. But what happens if the conservative approach fails. So this is the idea that starts from Penrose, which suggests that, well, perhaps these gravitational cat states should not be stable, they should not exist. The argument is that each component of a gravitational cat state will generate a different space-time, and there is no canonical way of relating time coordinates into different space-times. So there is no unique time variable. The notion of time is fuzzy in this state, and this ambiguity in the time evolution might be expressed as a loss of quantum coherence. This is a very interesting argument. It's not waterproof, right? But it is interesting and suggestive that perhaps quantum effects and gravity are very different from what we naively expect. Now, Laios Diosi, who was a student of Karoli Hazi, who was the first to deal with these questions, he proposed gravity-induced state reduction model in the late 80s. And this showed decoherence at the scale with the decoherence rate for a particle of mass m and radius r. The decoherence rate is given by this quantity. This means gravitational cat states are suppressed. They do not exist. We cannot see them. Even if we follow a protocol for their preparation, this protocol is going to fail, and not because of fundamental physical reasons. That's what this prediction is. And this is the same prediction with Penrose, so we call this theory, this prediction, Diosi-Penrose decoherence theory. As I said, Diosi goes through a master equation, Penrose goes through more general arguments that involve the consistency of general relativity. So it's a very, very robust prediction. It's a robust prediction because, as you can see here, there is no free parameter. So you have let's say we have a ball of mass m, radius r. These are measurable. You have g. There is no. It's a unique prediction given by already known constants. It has generated intense, very high interest. The Diosi model has been tested. It has been ruled out experimentally in its original version with no free parameters, but its regularized version with some regularization parameters in the denominator, because remember, we have to regularize the mass density to make it correct. So here we should put some regularization parameter. If it is sufficiently large, it survives experiments, but it's rather counterintuitive. And there are some other critique about that it is not natural to expect that the Newtonian gravity term is related to the ambiguity in time. But still, this is the most popular idea for decoherence. And this field of gravitational decoherence has seen strong interest in recent years, especially in the context of quantum foundations. Why? Because after the 80s, when we have Bell inequality experiments, they settled the issue of hidden variables. There are no local hidden variables compatible with quantum theory. The number one problem in quantum foundation is how does the classical world emerge? Known aspect of it is the quantum measurement problem. And what is exactly the classical quantum border? So most of the research, and especially the experiments that are trying to understand quantum theory, focuses on this question. And one possible answer is that there is some fundamental mechanism that suppresses superposition, like gravity-induced decoherence. So there are, in the last, let's say, 30 years, there has been a development of these decoherence models. Again, these decoherence models mostly deviate from what I call the naive expectation about the interaction between quantum and gravity. So there are essentially four classes of decoherence models. In one idea, like Diosi-Penrose, gravity is not quantum. Gravity is fundamentally a classical entity. There is no need to quantize. All attempts to quantize are misguided. And in this sense, if gravity is classical fundamentally, then it acts like a classical system coupled to a quantum system. So it gives some predictions that are very different from what one would get if we assume gravity to be also a quantum field. And one such theory is Joseph-Penrose theory. Another idea is a nonlinear equation for the wave function known as the Newton-Schrödinger equation. Some models using the language of quantum information channels. There's quite a lot of work in this direction, but this is not compatible with general relativity and quantum field theory. It's grossly incompatible with general relativity, as can be shown in these models. So not only do we have a modification of quantum theory and quantum field theory, but also these type of models seem to violate also the symmetries of general relativity. Now, there are some old proposals about the coherence from quantum gravity. The problem with these proposals is that if you have the coherence from quantum gravity, this should be what emerges from quantum gravity is predominantly GR. So if you have some Planck scale physics from quantum gravity, this should be beyond GR. So if indeed you have this type of phenomena, they are subdominant to GR. So let's first study GR and then see if there is some decoherence from subdominant processes. Now, there is very popular models is the decoherence from space-time fluctuations. Essentially, the idea is that at some scale, the Planck length distance is not well defined. This creates noise, and this noise may be manifested in the macroscopic scale. It can be seen in macroscopic quantum experiments. Again, it can be shown that this is not compatible with general relativity in the sense that they violate the crucial symmetry of general relativity, diffeomorphism invariance. These models, they treat space-time coordinates as noise and not as gauge variables. And finally, there is this model of decoherence, which has been worked by collaborators and by my work with Baylock-Hu and also independently by Miles Blencow. Essentially try to find the decoherence for quantum gravity, the coherence model that respects both QFT and GR. So we don't want to solve the measurement problem with this model. What we want to show is if there is a decoherence model that makes non-trivial assumptions and can tell us something new and fundamental. So the idea is that the coherence here is generated not by the modification of the Newtonian term, but by a stochastic background of gravitational waves. Now, Miles Blencow suggested that the origin of this background is cosmological, like inflation, but it is possible that it is also structural to gravity. There are some classes of theory that say that space-time emerges as a thermodynamic limit, and if indeed Minkowski space-time is obtained at the thermodynamic limit of some underlying theory, then the fluctuations around Minkowski are not quantum, they are thermodynamical. Thermodynamical fluctuations are much, much stronger than quantum, and this is what we're trying to model here. So this stochastic background of gravitational waves is supposed to be thermodynamic fluctuations of Minkowski spacetime. And the reason we did it is because it respects general relativity, and its test will give non-trivial information about the fundamental nature of gravity. Effectively, at weak energy, non-relativistic particle, we get this type of equation. So it's a master equation. This is the Hamiltonian term, and here we get a term that is induced by the stochastic gravitational waves. In one dimension, this is just a Hamiltonian, so it's a very simple equation. And we predict the coherence in the energy basis and not in the position basis. This means that the density matrix is diagonalized in the energy basis, while in Joseph-Penrose it's diagonalized in the position basis. There is one free parameter, which is the noise temperature of the perturbations, of this thermodynamically supposed perturbation. This is not, it's a noise temperature, so it's not a thermodynamic temperature. So being a noise temperature means an effective parameter that measures how strong the noise is, and it has the dimensions of energy. That's why we call it noise temperature. So in principle, theta may be larger than Planck temperature, but to have compatibility with cosmological and solar system physics, theta should be a few orders of magnitude smaller than the Planck temperature. So still, a few orders of magnitude smaller than the Planck temperature, it could be 10 to the 28 Kelvin. As I said, it's not a physical temperature, does not satisfy, let's say, the zeroth law. It's a noise temperature. Now, this model that we constructed is compatible with the existence of gravitational cat states because it creates decoherence in the energy basis and not in the position basis. So what about experiments? Now, there are many proposals for measuring Diosy-Penrose model starting from the beginning of the century. And there is a plan to carry out the macro experiments by the European Space Agency to test, well, not only Diosy-Penrose theory, but several models of gravitational decoherence. In fact, the European Space Agency has placed this type of experiments among the top 3 pure science priorities for the coming decade. And in our model, the EBH model, it can be tested in optomechanical experiments, which means you don't need to go to space. You can do it in desktop. So you need to construct a superposition of macroscopic distinct states with the energy difference of 10 to the minus 14 joule to see this. And it can be seen with matter wave interferometry in a different, and this probably requires space because we need to have a very large, a very long propagation distance, long interferometry, and I'm going to say explicitly that this might be possible in deep space experiments. And one thing we are working now is the extension of this model to photons. Photons interact much weaker with gravity, but they have the benefit that you can measure very small angles, very small interference phases. I mean, the LIGO for gravitational waves has a relative accuracy of the order to the 10 to the minus 9. So in principle, very small drops of coherence can test the EBH model and give us an effective parameter for this noise temperature. And one experiment that we are that is currently under proposal for NASA for the next decade is the Deep Space Quantum Link. So in principle, this is a program to test gravity and quantum in deep space. Experiments are planned for the Lunar Gateway Space Station, which is, well, it is expected to be ready by 2026. And the idea is to find, first to test gravity, how it interacts with quantum systems, both the conventional theories and the more, well, and the unconventional theories that involve gravitational decoherence. And this collaboration, we are currently at the stage of trying to enter the decadal, the NASA decadal for 2023-2032. As you can see, the DSQL, we are teams from all over the world, and you see, University of Patras and the Greek flag is here, where we are involved in the theoretical modeling of this project. So, what would happen if we see gravitational decoherence? Diosy-Penrose model has so strong violations of quantum theory and general relativity that if you really see this, this is a revolutionary implications. So even it means that both general relativity and quantum theory must change. So it's high stakes, but a priori rather implausible. Our model has not so many spectacular consequences, but still it gives non-trivial. It has non-trivial implications for cosmology and quantum gravity research. Certainly, if gravitational perturbations are fundamentally thermodynamic, some research programs on quantum gravity are falsified. But if these gravitational decoherence phenomena do not arise, then gravitational cat states exist. and it's something that we should observe in the tabletop experiments in the next decade. Otherwise, it's whether they exist or not, it's a win-win situation if we look for this phenomena, because we learn something new about the interplay of gravity and quantum theory. So there are many, many open issues on this field because, as I said, it's an emerging field, and it's very much related on how experiments, well, what the experimental possibilities are and which ones of them can be exported to space. So, and with that, I want to thank you. I'm concluding here.
We have applause again. So thank you very much for a very interesting talk. I think there will be questions, and usually we first take questions from the audience here.
Right.
Okay, I have two comments and a naive or simple question. Your talk reminded us of, the first comment is, it reminded us of Penrose's theory that conscience may have something to do with quantum gravity effects in the human brain. He wrote a book on that, The Emperor's New Mind, or things like that.
Right, yes.
And I don't know if any of what you talked about has this quantum decoherence. That's one comment. Maybe you can comment on that. The second comment is that stochastic gravitational wave background. If you say that it is cosmological, it seems natural that the size of those waves is much, much larger than the nanometer scale that you were discussing in the first part of the talk. And not only that, maybe that scale also evolves with cosmological time and that changes its effect. Maybe you can comment on that. And the third question is, do you think that if someone studies these problems with something like Bohmian mechanics, where you follow trajectories of particles with mass in a certain gravitational field, do you think that that might answer some of the questions you posed, Bohmian mechanics?
Right. So regarding the first, there is very indirect relation of what Penrose has said about the mind and his theory of decoherence. Essentially, well, I mean, essentially that these decoherence effects will also be present in the mind, but it's completely different regime. So in practice, it is not relevant to the present discussion. The second question, cosmological, yes, I don't think cosmological, you need a better model, let's say, for fluctuations in the cosmological case, and I don't think thermal is a good approximation. In fact, there are some suggestions that if you take gravitational background from cosmological and you take inflationary produced, say, gravitational waves, there is this idea that the fluctuations they induce might be enough to tell you whether these gravitational waves are actually quantum or classical. But as I said, I don't think the coherence from cosmological is very plausible. Just historically, Miles Blenkow started with that. And the third question was about Bohmian. Yes, Bohmian mechanics should give some predictions. Yes, it can get a coupling, it can get, you can write the interference experiment. Yes, it can get some predictions. I don't know if it will be identical with the ones, well, in principle, this should be the same with standard quantum theory, I suppose. Yes. But of course, it depends on how you treat the gravitational field. As I said, you assume, I mean, the conservative approach assumes that the gravitational field is quantized a conservative way. All other theories of decoherence, except our model, the AB8, assumes some strange rules for the quantization of the gravitational field.
Thank you.
Okay. Are there other questions from the audience? If not, is someone else who wants to ask something?
No, may I make a question?
Yes, I can see you. Yeah. Okay.
Yeah, Suhari.
Go ahead.
Fine, everything is fine. Well, I actually have two questions. The first one is related to the terminology gravity-induced decoherence. So if I understand well, the starting base for Penrose, let's say Diosy and so on, although Diosy changed course, I mean, over the years, is that if a particle, a single particle, is described by a wave function, then the basic question is how does this wave function gravitate? I mean, what's the gravity field and whether this can influence the particle itself. And if I understand it well, when you go to the mesoscopic scale, let's say 1 micron and 10 to the 10 atomic mass units that you mentioned before, the basic effect is that the quantum, let's say the gravity effect on the particle would suppress the spreading of the wave function that would naturally induce a change of the dispersion of the wave packet over time for the free, let's say, particle. But this effect is totally deterministic, is essentially described by kind of nonlinear Schrödinger equation. There is nothing stochastic in it.
Yes.
Although it behaves in the same way like decoherence, which has the same effect, let's say, of stopping the growth of wave packets and making them, keeping the small particles small altogether. Actually, it's a quite different mechanism. So is it correct to call it decoherence? This is my first question. Or is there something more in quantum decoherence than that?
Right. So this is the model, the Newton-Schrödinger equation. Well, it's usually lumped together with gravitational decoherence because it is an alternative quantum theory. So it's not an equation that is compatible with standard quantum theory. You have a nonlinear equation for psi. This is incompatible with Born's rule, probabilistic interpretation. So this equation, we put the main assumption in the derivation of this equation is gravity is fundamentally classical. That's why it is, I lumped it together with the decoherence of originating from classical gravity. It does predict some decoherence phenomena, but the mechanism, as we said, is very, very different. It's decoherence and mostly localization because of nonlinearities.
Yeah. Okay, and the second question is regarding the Girardi-Weber and Rimini theory, where you have, let's say, a fundamental stochastic process that produces the collapse or any of those phenomena. And now you mentioned fluctuations in space-time. So let's say the stochastic part of the gravity background itself. Could those two things be the same? I mean, could eventually the fundamental, I mean, Girardi's theory has a fundamental constant that tells you how many events should happen per unit of time on dependence of the number of degrees of freedom of the system and so on. But could that just be a phenomenological expression of just the nature of the background space-time?
In principle, you can. I mean, people usually want to separate those two because the GRW might have a different physical origin. So they prefer to have free parameters and constrain those parameters from experiment. So they do not find it necessary to relate to gravity. In principle, it could relate to gravity, yes. In principle, it could, but you see, GRW has a pragmatic, let's say, motivation to suppress macroscopic superpositions. So the main motive, the structure of the GRW terms are such as to guarantee the suppression of the superpositions, while the ones originating from gravity make some assumptions that is inherently space-time character or gravitational. They do not give exactly the same results, even though they are very they belong in the same, let's say, line of thought. But in principle, they are distinct and they are tested by distinct experiments. That's the key point.
Okay, thank you.
Okay, thank you, Christos. Are there any other questions? Not from what I see. So again, thank you very, very much for the very interesting
You're
talk
welcome.
and answering the questions. And we'll be in touch.
All right.
Bye-bye.
Bye.